Uh, yeah, just confirm if you're able to see the problem. Then I'll start the discussion. Okay, great. So you can see the problem. So the first problem was something like this. There was a story, and I won't get much into the story. I'll try to explain what the problem is by drawing a simple case, and then after that, if everybody understands the problem, then we can move on to the solution. So you have a matrix of zeros and ones. I'll fill up this matrix with some example values. So some of you can consider these matrices as bench, and some of these are occupied, and some of these are not occupied. Uh, in this particular problem, if it's occupied, the value of the matrix at that given point is 1. So if it's 0, then it's not occupied. So let's say the matrix is as follows. And now we want to tell, so the objective of this problem is to tell the closest distance between two particular seats that are not occupied. So closest distance between two particular seats, two particular elements in the matrix that have 0. In this particular example, we have 0 over here, we have a 0 over here, and we have another 0 over here. Just another quick confirmation, if you can see what I'm drawing over the screen.
Yes, sir, it's visible.
Okay. So we have 3 zeros in this example. And if you consider, like, among these 3 zeros, there are if you want to select 2 zeros out of these 3 zeros, let's say we have n zeros. So there are NC2 particular ways in which we can select 2 zeros, and then we can find the distance between them in order one time. So if we use a very brute force approach, we'll have to find the coordinates of all the zeros, xi, yi, and xj, yj, and all the zeros. And then we'll have to take NC2 particular pairs, and we'll have to consider minimum of that. So it would be an order number of zeros squared approach. And as the size of the matrix is n into m, so it would be n square approach. And this won't really pass the time limit. It should get time limit exceeded over here. So what we have to do is we have to find an optimal algorithm for this. And I'll move on to one node and I'll try to explain the intended solution. I'll share my OneNote screen, and then I'll ask for confirmation if you guys can see this. So just confirm once again if you can see this. Are you able to see this?
Yes, sir.
Okay. So again, I will draw the thing again. So the brute force approach was order n square m square, and now we'll try to optimize this to order n into m. And how would we be doing that? We'll be using something called multi-source BFS. And what we'll be doing is, let me try to explain with an example. So let's say we have a graph like this. And let's say these are the infected nodes on the graph. And the question is to find what would be the total number of infected nodes at the end of t seconds. So one way is to start a BFS from this one and go to this, and then go to this, and then go to this. So one way is to spread the infection starting from all the infected nodes, and like basically do a BFS from all infected nodes. From all infected nodes. An easier way and sometimes more effective way to do this is to use multi-source BFS. So what we do in this approach, we create a pseudo node. So this blue node, it's not a node in the graph. We call it a pseudo node. And we add an edge from this node to the infected nodes. And now we start the BFS from this pseudo node. So at t equals to 0, we are at this particular node. Let's say we only have, so when we create a pseudo node, we say the infection only exists at this node at t equal to 0. Now at t equal to 1, so we'll call this t equal to -1. At t equals to -1, the infection only exists over here. And as time progresses, so at t equal to 0, we start a BFS only from the pseudo node. So we need not start the BFS from all the infected nodes. We just start the BFS from the pseudo node. So at time equals to t equals to -1, we are over here. Only this node is infected. At time equals to 0, so this node is connected to this and this. So at time equals to 0, these two nodes would be infected. And this is exactly the condition that we were looking for. At time equals to 1, this node would be infected. This node would be infected. And this node would be infected. So let's say if the question asked us about are the number of nodes that are infected at time equal to 1, we'll start a multi-source BFS from the pseudo node and we'll count the total number of nodes that are infected. So the count would be 5. We'll be using a similar approach in this matrix example also. I'll zoom in and I'll try to show it over here. So 0 states empty seats. And I want to find the closest pair of empty seats. I'll create a pseudo node and so this is just a way of explaining the pseudo node thing. Implementation is a bit easy. It's not that tough. I will show you that also. So from this pseudo node, I'll run a BFS. And what I want to do is I want to find the two closest pair of empty seats. And as the BFS runs, so first it will visit these things, the empty seats. And then the BFS will progress in a layer by layer fashion. So in a layer by layer fashion, when the BFS, let's say the BFS from this node is progressing like this, and from another empty seat. So this was an empty seat, and this was another empty seat. And as I do the BFS it travels in a it goes by the level order. But whenever I find a particular node that I've already visited, so let's say when we start BFS, multi-source BFS from a pseudo node, and both these seats are empty, a BFS would be started from here, and a BFS would be started from here. And it will progress. Let's say this one will progress in left direction, this will progress in right direction. As soon as I have a node, common node in both these BFS, we can say that this particular node can be visited by both this one and this one over here. And as BFS progresses in layer by layer fashion, we are sure that this node is the first node that is visited in a layer by layer fashion. And therefore, this is the closest node to both the nodes. And using this, we can find a solution. So what we'll do is we'll start a multi-source BFS from all the empty seats. Now, as soon as I find a seat that is already visited, and the parent. So what I'm calling a parent over here is, let's say at a particular iteration in BFS, this is visited, this is visited, this is visited, this is visited, and for this, these four nodes will be visited. So I'll be calling the parent of this particular node to be this thing over here. So this thing that I'm marking with green, which was an empty seed, it's the parent of these particular nodes, because when we started BFS, the first time that this particular node got reached was from the BFS that originated from this particular empty seed. So I'm defining parent as this. So I start a multi-source BFS from all the empty seeds, and as soon as I find a seed which is already visited and the parent is different, and it would be different. So we need not consider this thing also. Okay, so it should be already visible. Visited. And if I find a node that is already visited, I'm sure that this particular node has been visited from another BFS, and I'm visiting this particular node from a second BFS. And as we discussed over here, that the first node that I find that is visited from two different BFSs is the node that is common to both, and these two particular empty seats would be the closest pair of seats. If you guys have any doubt, or maybe like if you didn't understand the question, you can speak up. Okay,
So just one doubt. Where you said that we just have to check if it is visited, we have to make a parent array right here. Like for every node, we'll have to check if the parent is different, because otherwise, yeah, it can loop.
Yeah, it will loop. So we have to check if it's already visited, and we have to also verify that the parents are different. So this particular node from which it's currently being visited is not equal to the node that like the parent of that particular node. So let's say I visit I comma j, and I know ki, let's say I'm visiting from x comma y to I comma j, and I already have a parent for x comma y. And as this particular node I comma j is already visited, it will also have a parent. So let's say pi, and I'll call the parent as px. If these two are not equal, then only, and if these two are not equal, then only I'll say ki this is a valid node for our comparison. So we'll consider the shortest distance between two unattended chairs as the Manhattan distance between px and py. Px and py. Yeah. So if anybody would like to share their own approach, if it was different from this particular one.
Sure, sir. Can I?
Sure.
Okay, so in my approach, I was actually confused at how will I create a graph from this, because as you can see, the constraints are too large to make it. Edges will be too much. That's why what I did was I basically just traverse the matrix from top to bottom and left to right format once, and wrote the closest neighbor that I have. Okay, so if I move one right from a empty seat, I'll just add one, and if I reach an empty seat again, I'll just start a zero from there again, and keep.
Can you please repeat? I think I didn't quite get it.
Yeah. Let's say we have a zero cell in this grid in, let's say 1 comma 1. Let us in 1 comma 1, let us write just 1 0, please. Can you?
Okay. So 1 0 in the whole matrix?
No, in 1, 1 at the index
Okay,
1, 1.
okay, at 1, 1.
Yeah. Here, and let's say we have one on the just last row in this column.
Okay, last in this column.
Yeah, we have a 0, 0 here, 0.
Okay, 0, 1.
And let's say, for example, we have one more 0 in the column just sorry, in the row just above, in column 5th, let's say.
Okay, so 1, 2, 3, 4, 5.
Yeah, let's say okay, it is okay. Now what we do is we just run
So all of
basic.
these other things are 1
Yeah,
block.
let's say we have these ones. Okay. Now I run two traversals from one from top to bottom and left to right. One
Okay.
from top to bottom, left to right. The other from top to bottom, but right to left.
Okay, so this one you are going top to bottom. So you are visiting
Yeah.
this one from here, then
Yeah.
here, then
Yeah.
here, and then
Yeah.
from this. Okay.
Yeah. In the first time we'll do this like this, and in the second time after we complete this, we'll do another one from top to bottom, but right to left.
Okay, so here, then here, then here, and then after
Yeah.
visiting this whole.
Yeah. Now what I did was, like, when I encountered the first 0, I'll like, if I haven't seen a 0 so far, then I'll just write infinity above, infinity there. For example, I will say that all the rows above and on the left side which aren't visible, like negative ones rows and columns, will all be considered infinity. And then I'll just, if I haven't encountered a 0, I will write the value lowest on above and left. And if I have encountered a 0, then I'll just increase write 0 there, because it is the closest, right?
So let's say you are traversing like from top to bottom and left to right. You encounter this 0 over here. So what will
Yeah.
you do now?
So I set a 0 here only, and on the, yeah, this node will be 0 itself, and on the right side I'll just add 1 from the its left and top, the minimum. Yeah. And when I go to again on the next row, I'll write infinity, because I haven't found a 0 previously and upperly. Like there is no 0 that is on the up or left, right?
Okay. So like if a cell is over here, there's no 0
Yeah.
in this whole region.
Yeah, there's no 0 in here, so I'll just write infinity.
Okay.
Because the closest 0 here is infinity, right? No, we don't have any 0 on the left and top. And again I found a 0, then I'll write 0, then there I'll just go 1. I'll go 1 and another 2, and now we have a 0 up, so I'll just write 1 here, because this is the minimum. And this way I just go down to the very right corner, updating the matrix. Like this is 1 1, so I'll write 2 here on this cell you're pointing to, right?
So you are going in basically all the directions, and okay, you're basically simulating a BFS, right?
Yeah, kind of. It's kind of a multi-source BFS only, but kind of different. Not with a pseudo node or something, but just a single traversal. And for every, I mean, if there is a solution pair of 0, 0, there must be 1 0 above or on the same level, and it can be either left or right. That's why I have to do two traversals, one from right to left and one from left to right.
Okay, nice. And this approach worked, like when you submitted?
I don't have to maintain a queue actually here, and it was kind of memory efficient as well. That's why I chose this. And it was also getting quite hard for me to make, like, catch up on a graph. How will I make it?
So this approach worked, like when you submitted it?
Yes, sir. It passed all cases.
Great. So for this particular approach, that was a good approach. It was space efficient as well. But like if I talk about multi-source BFS, the pseudo node thing, you don't really need to make a pseudo node. So for BFS, what you have a queue, and you push the first element, like the node from which you want to start BFS, you push that particular node into the queue. So let's say the queue is this, and you have three zeros in this matrix. So what you'll do is you'll push the positions of all these three zeros in the queue, and then you'll start the while loop. The while loop. So you have no while queue is not empty, and you perform the BFS inside that. So this is the only difference that you have in multi-source BFS than a normal BFS. You don't really need to create a pseudonode. You just push all the particular
Yes,
positions
sir,
of
I
zero.
got it.
Okay, so let's move on to the next problem. I'll share the screen again. Just confirm if you are able to see this. Are you able to see the Chrome screen?
Yes, sir.
Great. So now let's discuss the second problem. So in this problem, we are given a graph, and it's an undirected graph with n vertices and m edges, and the vertices are numbered from 0 to n minus 1. This graph is weighted, and each weight is a positive integer. So it can be from 1 to any number. So edge weight belongs to 1 to infinity. And you are given a list of edges along with the weights, but the list is damaged. Some of the weights read as 0. But we were given that all the weights are positive integers. So there's a catch. Whenever an edge weight is given to be 0, that particular edge has lost the weight. So it had a particular weight, W, but okay, I'll use a darker color over here. It had a this one. So it had a particular weight W, but it got lost. So our task is to give a weight to this edge. From 1 to infinity, we can give it any weight, such that we are given two vertices, S and T, and we want to give the assigned weights such that the shortest path between vertices L and T is exactly L. So, and we just need to tell if this is possible or not. So we'll have to answer yes or no. A tougher problem for this could be you can be asked to assign the weights also, just like just not yes or no. You'll be asked to assign also. So maybe after we discuss this, you can try the second part, or let's say the harder version, where you'll also have to assign the weights. You need not just comment yes or no. And so, does anybody have a problem understanding the question? Okay, looks like everybody understood the question. I'll move over to the OneNote screen. Okay. So can you guys see the screen now? It's glitching.
Yes, sir, visible.
Just a second. Okay. So let's say I have a graph like this. And these are the edges that are given to me: W1, W2, W3, W4. And let's say this particular edge has lost its weight, like it has lost its weight. So we don't know its weight yet. And let's say this one also has lost its weight. So we'll place a question mark over here also. So yeah, W2, 3, W4. and we don't know the weights of these particular two edges. And let's say this is S and this is, let's say this is T. Maybe we can have a more complex graph also. Like, let me make a more complex graph. And yeah, so all the nodes that are marked with red are ones that have lost their weight, and I've also marked S and T over there. So we need to tell if we can assign weights in certain order. So what we need to do is we need to assign. So we need not assign particular weights over here. We just need to tell if it's possible or not. We need to assign weights such that distance, shortest path between S and T is equal to N. So it's exactly N, not less than or not greater than. So the shortest path, shortest distance from S to T is N. Okay. So for starters, let's just run the shortest path algorithm, Dijkstra algorithm from S and then from T, and let's just find the shortest path from all the nodes S, like all the nodes from node S and all the nodes from node T. I'll just take a minute over here and get the code also, so maybe you can then understand a bit better. So, okay. So let's just go over the code and maybe we can understand both of these side by side. So N is the number of nodes in the graph and M are the number of edges in the graph. So this is edges and these are nodes. And for each particular edge, we take the starting point of the edge, the ending point of the edge, or let's not call them starting or ending point because it's not a directed graph. Let's say the end points of the edge, and W is the weight. Now, if W is greater than 0, so this if conditional statement would be true. If W is greater than 0, we'll add a edge into the graph, and if it's not greater than 0, then we'll store the edge in certain ways. So what we'll be having is EW is an array, and we have these arrays. Okay. So these store the endpoints. EW store the weight of this array, weight of this edge, and these store the endpoints of this edge. So if I say EW1, this would give me, and all these edges are the ones that have lost their weight. So EW1, it will give me the weight of the edge, weight of the first edge that we encountered while taking input that has lost its weight. So it will give me this. Initially, when we are taking the input, we are having all these as infinity. And this will give me the endpoints of the edge, the first edge that we encountered that has lost its weight. So endpoints. Okay. So the first thing that we'll do is we'll run the Dijkstra's algorithm starting from T and starting from S individually. Just a second. So yeah, and this is a simple implementation of the Dijkstra's algorithm. The different thing that we have is over here, and the use of this particular line would come out at like a later stage. Let's not get into it right now. So when we call this function for distance 0, s, 0 and 0, so this is x, this is y in this particular Dijkstra's function. This particular line won't be executed because x and sorry, 0 and 0 is basically 0. So this particular line won't be executed right now. Let's just wait and maybe we can find when this particular line will be executed and why. So yeah, so once you run the Dijkstra's algorithm for both these particular starting points s and t, we'll know the shortest length of the shortest path from S and T to all the particular nodes. And I'll store these in a 2D matrix. So this is a matrix that has 2 rows and a lot of columns. So this particular would be the 0th row, this would be the first row, and it would contain the shortest distance from S to all the other nodes, and this will contain the shortest distance from T to all the other nodes. Now, yeah. So what we'll do is we'll eliminate all the choices that are impossible. Like we'll eliminate impossible conditions, and then the conditions left with us would be possible, and then we can just output yes. So when would this not be possible? When can we not assign weights to edges such that positive weights to edges? So another thing to keep in mind, these weights that we assign should be positive. So for example, let's say distance from S to T, shortest path from S to T is less than N. So without even assigning these weights, initially all these weights are 0, and still we find that the shortest path is just a second. So we haven't added these edges yet in the graph. We have only added the edges where the weight is greater than 0. So even before assigning weights to these edges, if we find that the shortest distance is less than n, so if we assign some particular weight to these edges, and this weight is a positive weight, we are pretty sure that the shortest path will not decrease. The shortest path will not decrease. And so even before assigning, we have the shortest path less than n. So now, even after we assign, we can't really have the shortest path to be from S to T to be n. So if we find this condition, we'll just output no. Let's say if we find that we can reach from S to T, and the shortest path is of length L. We have already found the path, and we'll output yes. In this part of the code, we'll be working on the edges that for which we don't yet know the weight of, and we'll try to assign the weights in certain way. So I'll just take a minute. Can I I'll just have a glass of water. I'll get back in 2 minutes. Yeah, so I'll just continue from where we left off. Are you able to see the screen?
Yes, sir.
Right. So now what we want to do is we want to handle these edges that have a particular weight, like a weight which we don't know. We want to assign weights in a certain order. And we'll iterate over all these particular edges. We have total this particular, so we have these number of edges that for which we don't know the weight of because we counted them over here. And as we iterate over these edges, EU, this thing will be one of the endpoints of a particular edge that we are iterating over currently. This would be the other endpoint of that particular edge that we are iterating over currently. So what does this term mean? This means the shortest distance to this particular endpoint starting from S. And this thing over here, this thing, it means the shortest distance starting from T to reach this particular endpoint. Now, let's say the value of this thing plus this thing. So both these distances, if I add them, it's still less than equal to N. Now, what we can do is, I know starting from S, I can reach this particular node, let's say X, and I have this node for which we don't know the weight. And yeah, so I'm making directed edges over here, but these are undirected edges. You can visit them in any order. So let's say X is one of the endpoint and Y is one of the endpoint. I'm sure that I can reach this in D1 distance. Shortest distance is D1. And from T to Y is shortest distance is D2. And I have this particular edge for which we don't know the weight. Now I want this particular condition to be true. And as sum of D1 and D2 is less than L, I need to add something to D1 plus D2 such that I can make it exactly equal to L. So what I can do is I can assign this thing to be equal to this. So we need, let's say L was 10 and D1 was 2 and D2 was 5. So the shortest path right now that we got from S to X is 2 and from T to Y is 5. I need to assign this particular weight to be 10 minus 2 plus 5 for shortest path from S to T to be equal to 10. So if I assign this 3, so now the shortest path from S to T would be equal to D1 plus D2 plus 3 and this would be 10. And we exactly wanted this. So if we find that the sum of these particular two distances is less than, we can assign the edge in a certain way that we discussed, N minus sum of these distances. And now we are sure that we can have this particular path as the shortest path. And we'll return. If this is not true, if this particular thing is not true, we'll try it the other way around. We'll say we are trying to visit Y from S and X from T, and we want to assign this particular weight W. So the same thing, but X and Y are switched up because we don't really know the order in which they are in the shortest path. So we'll have to try both of these. So even if one of them works, we'll assign the edge a particular weight and then we'll return. Now, if both of these don't work, so the sum of both these paths is greater than M, there's no such weight that we can assign to this particular edge that will help us attain this particular condition that we wanted to. So what we'll do is we'll assign the minimum possible weight that we can assign this edge. So as all the edges need to be positive, we'll assign 1 to this particular edge, and we'll continue. So we'll update the. I think there's a more efficient solution to this, but like in this implementation that we used over the NPTEL platform, I think this might not be the most efficient implementation. Maybe I can get back to you guys with a more efficient implementation for this. But after I assign the edge weight 1 to this particular edge, I'll again update the distance array using 2 Dijkstra calls. And yeah, I for every particular edge, you can see that we can either assign it a particular weight such that the sum can be equal to n, or we can't. So if we can't, we just give it the minimum possible weight that we can. And yeah, in the end, we check if we can again reach from S to T using using a path of this like weight L, total weight L. We'll print yes, otherwise we'll print no. So if anybody would like to share any other approach or maybe a better implementation or more efficient implementation for this, we can maybe share. Or if they had any doubt for this particular question.
Sure. So may I tell my implementation?
Yeah, sure.
Yes. Okay. So what I did was I just ran a basic Dijkstra algorithm, just with a slight modification that for every every vertex that I reach on the shortest path, I keep a count. I keep a just a boolean variable for every edge, like in an array, to check if that route has a broken edge or not.
Okay,
So
let's say you start Dijkstra from this
S,
particular edge. So
then
you'll
for
have
the
0 over here, 1, 0.
yeah,
Okay.
not for this edge, but for the route that I took. Like from the Dijkstra, every node has a shortest route, right? For every route the node that I reach, I have a shortest route that I took.
Okay,
Let's say for
the shortest route that you took, yeah.
I just kept like for every node that if I took the shortest path from source to this node, does it has a broken edge or not?
Okay,
I
okay,
keep
yeah, makes
yeah,
sense.
and there until the end that I reach T, I just keep traversing through the Dijkstra, and also I just keep a imaginable weight of 0 for every broken edge, like it was given in the question that they are giving us 0 weight for every broken edge, right? Now, when I reach at the end, I just check 2 or 3 conditions. Like if the shortest weight I found is greater than L, then it is doomed to be not possible, right?
Yeah, because even if you assign all the weights as
To be
minimum as
0,
possible, yeah.
yeah, then also it will go out of bound. Now I check if the shortest path I found has has a weight less than L, but the path doesn't has any broken edges in it, then we can't assign any weight ourselves, and therefore it all will also be a false case.
Yeah, makes
Otherwise,
sense.
yeah, if it is less than L and we have at least 1 broken edge, then we can assign the remaining weight to it, and it will be a true case.
Yeah, makes sense, makes sense. So
Yeah,
did it pass like the cases for the
yeah,
problem?
so it passed all.
Yeah, that's a really nice approach, and yeah, a really simple one as well. So
Yes.
I'll just reiterate if someone would want to listen over the approach again. What he did was started a BFS from, let's say, S. Started the Dijkstra's algorithm from S, and for each particular node that he visited, he'll give a count on the number of broken. Maybe not the count. He needs at least one. So he'll give a Boolean array, as he says. So he'll give a Boolean array if during visiting this particular node from the shortest path, if he had a broken edge in between. So if he has, he'll put true, and if he didn't, he'll put false. And let's say after he visits from S to T, uh, he'll know the shortest path that like the weight of the shortest path that zero. Initially, he put all the weights of the broken edges as zeros. So let's say from S to T, the distance that he found was greater than L. So there's no way that he can assign weights to these edges, positive weights to these edges, such that the shortest path decrease. So it will never decrease. Even after you assign the weights, it can never decrease. The only thing that can happen is it can increase or stay the same. So for this particular case, our answer would always be false, or you can say no. If it's less than L, we need to increase. We need to increase the length of the shortest path. So now, if we don't have any broken edges in between from S to T, the answer would be false because we can't really increase the path in any other way. We increase the shortest length of the shortest path. If it's less than L and we have a broken edge, then we can assign weights to that broken edge using this particular thing that we discussed over here, something like this. Yeah. So another case I think that we can consider, we might have considered. So did you consider equal to L and then if you
Yes,
find
I was just about to tell this. So here, in case I have a node there where I have two paths, one that are of equal distance and one has a broken edge in between and one doesn't have, then
you'll
I'll
consider
consider
one with broken edge,
no,
right?
I'll consider one with no broken edge, right? Because in
Uh,
the other one, if I put like let's say a weight of one, then the other one will be the shorter, right? With no broken
uh,
edge.
I didn't get it. Can you please repeat? If you like for a particular node, you will have two
Uh,
paths that have the same
yeah,
length,
I have
and
two paths that have same length,
Mhm.
and one has a edge and the other has no broken edge. Then I
Mhm.
can reach to that node from the no broken edge path in definitely this time. And the other
Mhm.
path that I took is already on its least possible value, right? If I add a value, it would obviously be greater, like one or two or maybe anything, but it would definitely be greater. So I will like flag this with a path that has no broken edge in between.
Yeah, that makes sense because so if it's equal to L, you'll have to make sure that
Yeah.
it does not increase anymore. So you'll take the one with
Yeah.
no broken edges.
Hmm. Also, sorry, I think you here in this case, if the path that I found is equal to L, then I can assign zero weight to every broken edge, and therefore it will be a true case.
For the final thing, yeah, you
Yeah,
can.
yeah, yeah.
So if anybody would like to share another approach that they might have used or want to discuss something else from both these problems, they can speak up now. If not, then we can maybe close the session for today. Great. Looks like nobody has any further doubts. So thank you everyone for joining in for the week 6 programming problem discussion. And we'll meet again for week 7 discussion next week, I suppose. And yeah, we'll discuss this problem next week. Thank you for joining everybody.
Thanks a lot, sir.
Thank you.